So some of you met me before. I'm Maxwell Flitton, senior Rust developer here at Surreal. Also wrote the book Rust and Web Programming, fusing Python with Rust, and currently writing the O'Reilly book for async Rust with Caroline Morton, which is a doctor you saw on the stage. So we're doing a lot of really exciting work, and a lot of the stuff that we're doing in the upcoming books kind of filters its way into this work as well. So it's quite exciting things. So what I'd like to talk to you about is we got to set the scene a little bit first. Let's go back to like the early 2000s. And I really like listening to talks by data archivists. It's a bit weird, I understand, but I'm a software engineer at a database company, so data persistence is going to be a bit more interesting to me than the average person. But they will try and tell you how to store data for as long as possible. And that's what they're obsessed with. And they usually find them in universities and libraries and all this sort of thing. And they'll give you these different types that you can have. So there are still people that use floppy disks. It's kind of out-fashioned now, but they still use them. And we have these CDs as well. But they're very obsolete, and they degrade quite quickly, and they scratch, right? So in the 2000s, there were people taking pictures on their cameras and uploading them onto their PCs. And they found that these would get scratched, if anyone can remember that. Everyone's had a scratch CD at one point, right? So we kind of go on to SSDs and spinning hard drives, and they'll say, okay, SSDs, they're fast read and writes, so you want them in your computer, but if you want to store stuff for a really long time, really, you want to store it on a spinning disk. They're kind of the best, but they're slower read and writes. But that's not enough for a data archivist. They'll say, you can't just have one, you have to have two, you have to have dual RAID. So you have to write your data to two hard drives. And then if one breaks, then you get a new one, slot it in, and you duplicate it over. So then that's not really enough for a data archivist. They'll say you have to replace these drives every 5 years, maximum. And that's because these read heads and so on start to break, and the disks start to degrade. Now, honestly, who does this, right? I don't know many people who do. I tried to do it myself. It didn't work. I lost some data. But, in the year 2000, everyone was trying to do this, and it just, everyone's lost some data. Everyone's lost some photos. So we kind of moved over to the cloud, and this is it took a while. People said, what was the cloud? People still, I think, sometimes don't understand it, and there was a bit of a pushback, and I was one of them. I was very arrogantly saying, I'm going to get a dual RAID hard drive, and I'm going to do it myself, and then I lost one of the drives. And eventually, I was like, now I've got a Dropbox subscription. And we don't even trust people enough, really, for that. So our phones, they automatically sync, right? They just automatically sync our photos to the cloud, and I'm very grateful for that, because I can't even do that myself. But why are we talking about this? Because I'm talking to you about machine learning. And it's because I would really argue that in terms of machine learning, we're still in this floppy disk state, CD state, where we kind of store our machine learning models, but they're just like kind of ropey in the way that we store them. So what we have here is we have a Python script that we kind of build, and this is where we write all our logic. Then we train our machine learning model, and then it goes into weights. So people who are not that familiar with machine learning, there's just a series of matrices, and then you just put some inputs in, and then you multiply the matrices in a series, and then you get a prediction. And that's machine learning, essentially. There's all these fancy ways of training it, but that's essentially what it is. And then in Python, we have this thing called Pickle. And it's a bit of a weird name to get used to, but what you do is you serialize your raw Python object, called Pickle, that's the serialization, and then we store that on disk. And it's really easy. Everyone uses it, when they're trying to do store persistence and that sort of thing. And I used it when I started doing initially machine learning. Everyone likes to talk about really fancy things like TensorFlows, just storing the weights, doing PyTorch. But in reality, what I've seen under the hood in some of these, machine learning companies is they just store it in Pickle. And what marketing says and what actually happens under the hood is very different. So we know this, right? So pickling is actually really bad. It's easy, but it's really bad, right? So it's very insecure. And what I mean by that is that you can write anything, really. You can write any sort of Python object, and then you get it to write any sort of logic that you want, and the person will just load it. So there's a thing called a pickle bomb if you want to you look into it, you can create your own pickle bomb. And let's say that I pickle my machine learning model, and then I store it in pickle, in a pickle file, and you swap that with your own pickle file. Now my code will break because your code won't do exactly what I'm expecting, but you can run anything you want in your code before my code breaks. So that's kind of dangerous. Insecurity as well doesn't just mean someone hacking, because I would argue that you've got bigger problems if someone's going directly into your data store and altering things around. But you could just like load the wrong model, the wrong version of the model, or put the wrong inputs in. You just don't really know, right? Especially if it executes. And this kind of goes back to like my experience. So before I was a software engineer, I did physics and then went into software engineering. I was an A&E nurse for quite a while, so I have quite a varied life. And people always think that errors happen in medicine through very complex, convoluted things. And you see these TV dramas, and everything's, you know, Dr. House, you have to kind of work things out. But actually, the majority of medical errors that you see are just because someone forgot to note something down or forgot to, you know, put a wristband. If you really want to drastically increase the risk of a medical error happening to you as a patient, take your wristband off, right? That is, you know, the chances of getting the wrong drug or something just shoot through the roof. And we're humans, this is why it happens. So it also happens if you just start chucking around machine learning models in these pickle files and you don't really know what these pickle files are. And so you say, trust me, that this is the right model and this is the right inputs. You're gonna get some errors, right? And this is the thing that's also under the hood. You know, machine learning companies don't brag about this. They don't say, we got the machine learning models mixed up and all this sort of stuff. They'll just keep it quiet, you know? So again, it's that difference between marketing and what actually happens. So, oh, I've kind of skipped a slide there, sorry. Pickling is bad. Brittle. Oh, and it's coupled. Sorry, this is the other thing. So coupling, there are some people that I've seen in some of these companies, and they try to solve those problems, right? So they write wrappers around their models, and they say, look, we're being really smart. We've written an object around the model that we're pickling, and then it's got some sort of extra logic that does the checks. But then these usually interface with other parts of the code. And then you've got this like very brittle nature in these coupled models. So I've actually seen it. And again, this machine learning company didn't brag about it, so you most probably don't know it happened. And they wrote all these wrappers with these data interfaces around their pickled models, and then their code changed, and it broke the loading because it was referencing code that was no longer there. And they had to use Git versioning and completely reverse their, you know, system so they could start using the machine learning models again. And sorry, what I see now in some of these companies is that they wrap an entire Docker image for each model for this. And that's safe at least, but obviously it's not very efficient. So we kind of moved to building a SORML file. What this does is essentially we still have the Python, we still make the machine, you know, define a machine learning model, we still train the weights, but then we have like some text as a header. And we picked text because it's not very cool, you know, if I tell you there's some text in front of the file, but it means that it's really easy to read, and we just want to like die down the hype in this field and try and get it so we try and reduce the errors and it's really easy. So you can load it, you'll see some garbled mess where the model is, and if you can read binary, you're definitely smarter than I am, but you'll see some plain text and it'll have all the information there, so you say, I know exactly what this model is doing, I know what the inputs are, that sort of stuff. And then we combine it. So right now we have PyTorch, and we're relying on a PyTorch runtime. And what this is then is our text header. So you load the text header, you start to work out what's going on in the model, and then you start loading the model. And we have Python bindings, and we also have the majority of it written in Rust. So that means that if you have Python, you can just load the data, you know, you can load the model, sorry, and just run it in Python. But also, if you have Rust installed, you can just load it and run it in Rust. But because SurrealDB is written in Rust, that means that it also just runs on our database as well, which is what the main goal is. So here we've got how to actually define a PyTorch model. And maybe is it big enough? I think it is, right? So this is a standard, you know, classic way of introducing people to machine learning. So you say, I'm going to do linear regression. It's a very basic model. And we say, OK, we're going to make up some data, and it's we're going to try and predict the price of a building or a house or whatever you want to try and buy. And it's square foot number of floors, and house price. Right? So, and we're trying to predict the house price, and we have the square foot and number of floors. Now, obviously, we just know that there's some sort of correlation there. So we normalize it as well. We don't always do that, but sometimes we normalize the data so we get a nice gradient descent. We don't get stuck in local minimas and maximas. But then you have to normalize inputs going in if you do that. So you're kind of corrupting the data technically, but you're making the training much smoother. And you will get accurate results if you normalize your data. So we define it, and we use PyTorch because we're only focusing right now on storing. We don't want to claim that we've reinvented machine learning. We're not going to tell you that we've got something that kind of trains the whole system. No, these guys work very hard. You know, these languages and these packages are really, you know, there's a lot of hours go into them, and they're really good at what they do. So you still use your PyTorch. So we've got a linear regression here, and what we do with this is we then train the model. So what we do is we loop through, and we have an optimizer or a regressor, and that's a certain algorithm where we try and we put all these inputs in, and we have some outputs that we test against, and we just keep iterating and changing the weights until we get the least error. And that's essentially it, right? Weights that are fine-tuned so we get a prediction. And none of this should be new if someone actually does this in PyTorch. And then we're just going to put some inputs in and just print them out just to see if it works. And this is in the documentation that we will release when this gets released. And then this is our CRMR file, right? So this is the Python bindings. And as you can see, that we add a description. It's nice to have. You don't have to add a description. This package is not going to fall apart if you don't put any metadata in, but it kind of defeats the purpose of why you're using it if you're not. And then we put a version in, and the reason why we put versioning in is that then you can have different versions in your database, right? So you can start to just compare two versions. Then we add these columns. So we've got the square foot and we've got the number of floors. And these have to be done in order because you have to have an order of input in that sense. And then we add some optimizers and we add some normalizers, sorry, and we add an output as well. And that essentially tells us everything that we need to know, and we save it. So if we want to use it, we just do the load, and then we've got two types of ways in which you can do the computation. So we have a raw computation, and this is because people do all sorts of fancy things in machine learning, and it would be very arrogant of us to say, look, do it our way or the highway. We know exactly what's good for you. Some people are doing like 2-dimensional vectors, 3-dimensional vectors, all this sort of stuff, right? So there is a raw compute where you just say, look, I'm sure you know what you're doing. You just put your raw data in, right? You've got to do whatever it is that you want, and you just get raw data out. But then we have what we call a buffered compute. And this is kind of like, it will start to map all the inputs with all the metadata and start to apply normalizers if they're there, and then you get a response, right? So this is very much like you'd recommend, if you're just doing columnar data and trying to predict something from just some columns, you can send this to a colleague and you can say, just do the buffered compute, just put these in. You don't have to do any normalization. You don't have to know any parameters. It's fine, and you'll get the output there. So with this, you don't have to worry about the insecurity. You don't have to worry about the brittleness because we're using PyTorch, right, which is a traced C model. So we can load it in any Python version that we want. It doesn't matter. And that's the other thing with Pickle is that you can sometimes, if you save it in one Python version and load it in another, you can get some corruption. Or if you start to have certain dependencies in your code when you're trying to do these wrappers and so on, and then you update your dependencies in your system, you can also get those errors, right? So we don't have to worry about that. And then we've got the version control as well. And version control I've seen in live models is quite a big thing, because when you're putting a new model in, people start to freak out. They're like, oh, is it actually doing what I'm supposed to be doing, right? And I've seen this in financial tech. There was a machine learning model that was trying to make predictions and make financial decisions on this, and every time they put out a new model, people were freaking out and constantly checking the database, and then it would be a bit of manual work to revert it back. This is quite a few years ago. I hope the system's improved, but this is actually what people are doing, right? They're not publicly telling you this, but this is how it works sometimes. And it gets rid of all of those. So let's say that we want to upload the model now. So we have a to and from bytes in our file, right? So we can just convert it to bytes, and I've used this example, so you can also use it for other things, because we've got an endpoint that's coming where you can just upload it, and we're also defining it in our SurrealQL, but you may just want to put it on a server and run it yourself, right? So you can transfer it over HTTP. You've got the 2 bytes, you just put it in the body, you chuck it over. And then we can also call it. So these are the endpoints that we're testing with, and again, it will go into the SurrealQL, so you can just run it in SurrealQL, and we just do HTTP calls, and you just send your parameters in JSON, and you'll get that. So what is next, and this is quite cool, is the logic, right? So because we're in SurrealQL, we can start to do a lot of really cool things, and this is just a prime example. So here we can say that we get the name and the age, and then we're going to do the ML, and we've got some sort of model called insurance prediction. I quite like insurance. That's I used to work in insurance, calculating financial risks. And we've got the version as well. So we pass in the age, the disposable income, which we get from the income, and purchase before, and you can see here that we're using data from like another table, so whether they've purchased a property, and if they've purchased a property, if it's above 0, right? So you've got a lot of logic there just in the SurrealQL. And because it's running in the database, it's right next to the data, so you don't have to like transfer data to and from. And we always want to try and reduce that, right? Because what we remember is that when we transfer stuff over a network, it has to go through a network card, and you have to serialize the data, then you have to deserialize the data, and it's usually like 10 times the amount of work than just a memory call. So having your machine learning algorithm running data right next to the data itself is way more performant in this sense. So this is something that I'm also quite excited by, and it is that it also works with sklearn. So sklearn, I quite like it. So people who maybe are not familiar with it, when I just started out, I used to try and use TensorFlow, and I used to brag, I could use TensorFlow and all this sort of stuff. Then you put the stuff on a platform, and you've got to maintain that stuff, and as you get older, you're just like, oh, just give me the simplest thing that I can do to implement, right? And sklearn just works out the box, right? It's not fancy. It doesn't tout the same like power, where you can distribute it over multiple GPUs or anything like that. It just runs on your CPU, but it works. It's just really easy. You just pickle it at the end. So I'm very happy that we tried and succeeded in terms of getting sklearn into it. And here you can see you have a random forest, and random forests are used quite a lot. Decision trees are used quite a lot in production. They're quite successful. And then we transpile it over to a PyTorch model. So we get away, we rip out that Python dependency and that pickle dependency, and then it gets stored just alongside our PyTorch models as well. So you can get your sklearn models, and you can just store them in the Rust database, or you can just load them with other Python versions. You don't have to worry about that pickle stuff. And this is something that's a bit in the future, and before we go on that, I just forgot. We kind of built the sklearn in interoperability of Microsoft's Hummingbird package and research, right, where they did a lot of the hard work and how it transpiles. I don't want to take credit for that. I'd love to, but the internet exists. You guys will Google it, and then you'll be like, what was he talking about, right? So these are our Python bindings in here. And you can see, right, when we do the save model, you can see there's a file path, but there's also a file ID. And then there's like a Python state. And what's actually happening is that we keep the logic, pretty much all the logic, in Rust. And this is why I call the Python bindings thin. So when you're doing anything, you're literally just passing an ID that's been generated in the Rust part of the client. And then you're just doing all your interactions there. And you're passing bits of data from Python. And the reason why we picked this is that then it's going to make it very easy in the future to start doing bindings for JavaScript or Ruby or Go, and we just employ those thin bindings as well. If we try and do as much as we can in Rust, and we pretty much do everything in Rust, then having interoperability between other languages then becomes very easy, and we can start to bolt them on at a very quick rate, and they don't need like a lot of unit testing, because they're literally just calling the Rust. So that's kind of like what we want to push forward in the future. So that means that we can have interoperability of machine learning files with all the major languages. And this is the final one. We are looking for collaborations. I really want to, people who have, machine learning models in production, I really want you to come and talk to me if you're interested in collaborating. Because again, I keep saying, with machine learning, what people say publicly and what goes on under the hood is very different. We want to work with people who actually have them in production, and we want to do all the boring stuff with you, so you can have a smooth integration and deployment. And working with collaborators in this sense means that we get better feedback and we actually hit the pain points and properly and solve them. Like if we just opened up the newspaper and just saw whatever was hot with machine learning, we'd have a really garbled kind of vision and direction. So if you do want to collaborate with us, we will help you with your version control. We're trying to work with removing the need for a runtime completely for more and more models. And then that means that we can go towards like WASM embedding and stuff like this, so you can run these in the browser as well. We're also working on async networking for large files, and this is why I referenced the O'Reilly book. So we're writing the O'Reilly book for async Rust, and we're trying to implement some of these things into transferring large files so you don't get that painful thing, in terms of like sending huge models, because some of these models are huge, right? They can get into the gigabytes and hundreds of gigabytes sometimes. And we're working for bindings of other languages and quality control monitoring. So when we go back and we think about that Serial QL, we did it where we just use it for an extra thing, but because you have all this extra logic, and you have the version control, you can just slot in like an extra like a parameter or an extra like row where you have a different version of the same model. And you can have them just running next to each other, right? Because these kind of all build on each other. Because you're not doing all this network calling and you're not doing all this serialization, you can just like rack them up, right? You can just say, look, I'm going to have 3 versions just running on this query next to each other, and I'm going to see what the outputs are. But you can also include them in queries. So you could just have the data, and then you could do one query with one, and you could infer a certain column, and you can have one query with just one version, and then you can have another query with another version, and then you can just compare the differences. So you can see very easily how you can compare the outcomes of monitoring of your machine learning models. And that's pretty much it. Thanks. Thank you.